The scene opens on a serene Siberian forest at dawn. The first light of day gently illuminates the vast expanse of trees. Mist hangs low among the ancient pines, creating an ethereal atmosphere. This untouched landscape showcases the remote beauty of the region. The pristine environment highlights the natural state before any significant event. The tranquil dawn underscores the untouched nature of the Siberian wilderness. An atmospheric explosion simulation begins with a sudden, intense burst of light. This initial flash signifies the point of detonation within the atmosphere. Immediately following the flash, a powerful shock wave rapidly expands outward. The shock wave propagates through the air, displacing surrounding gases. This visual demonstrates the immediate and dynamic effects of an atmospheric event. The expanding shockwave illustrates the transfer of energy from the explosion. A simulation visualizes the impact of a powerful blast event within a forest environment. The simulation focuses on demonstrating the destructive force emanating from a central point. Trees within the simulated forest are depicted reacting to the blast wave. They are shown collapsing in a radial pattern, moving outwards from the blast's origin. This radial collapse illustrates the directional and widespread impact of the destructive energy. The visual serves to quantify and understand the physical effects of such an event on structures. An aerial perspective reveals the extensive impact of a destructive event. The landscape below shows a vast area where trees have been completely flattened. This widespread devastation highlights the immense force unleashed by the incident. From above, the sheer scale of the destruction becomes starkly apparent. The uniform direction of the fallen trees suggests a powerful, singular force. This visual evidence underscores the catastrophic nature of the event on the environment. A text overlay introduces a central mystery, a powerful atmospheric explosion. This event caused widespread destruction across a significant area. Despite the immense impact, there was no obvious crater left behind. This absence of a crater challenges conventional understanding of large impact events. The phenomenon presents a scientific puzzle regarding its origin and mechanics. A perplexing aspect of the site is the complete absence of any intact objects. Despite extensive investigation, no whole artifacts or structures have been recovered. This lack of intact evidence poses significant challenges for analysis and understanding. The phenomenon suggests unusual destructive forces or a thorough removal of materials. Earth is constantly exposed to potential impacts from celestial objects in space. These impacts can range from small dust particles to large asteroids or comets. The force of an impact depends on the object's mass, velocity, and composition. Objects can leave significant craters or disintegrate upon atmospheric entry, leaving little trace. On the 30th of June 1908, a significant historical event occurred in Siberia. A massive explosion took place near the Podkamenaya Tunguska River. This incident, known as the Tunguska event, remains a notable mystery. It is one of the largest impact events on Earth in recorded history. The blast site was situated in a geographically remote area, far from human settlements. This extreme isolation significantly limited the potential for direct human exposure to the event. Consequently, there were no confirmed direct human fatalities reported from the incident. The absence of casualties underscores the profound remoteness of the affected location. Catastrophic events can exert immense power, leading to widespread environmental devastation. Such events are capable of directly causing the death of various wildlife species. The immediate impact includes the destruction of habitats and ecosystems. Landscapes are profoundly altered, often beyond immediate recognition or recovery. These changes demonstrate the severe ecological consequences of powerful natural phenomena. The long-term effects can disrupt biodiversity and ecological balance for extended periods. Environmental destruction can lead to significant and widespread damage to natural ecosystems. One example of such impact is the destruction of forest areas, often caused by natural disasters or human activity. Historical data, such as that compiled by NASA, provides insights into the scale of these events. For instance, approximately 830 square miles of forest have been documented as destroyed in a single event. This figure illustrates the immense scale of environmental impact and the resulting loss of natural habitats. The scale of environmental destruction can be quantified through various metrics. One significant indicator of physical damage is the number of trees destroyed. In certain events, an estimated 80 million trees were reported as knocked down. This figure serves as a widely cited estimate of the immediate physical impact. The loss of such a vast number of trees has profound ecological consequences. This destruction highlights the severity of the event and its environmental toll. The energy released by the blast is subject to varying estimates. These estimates provide a range of potential magnitudes for the event. Different sources may offer distinct calculations regarding the blast's power. Britannica, a notable reference, provides an upper estimate for the energy. This upper estimate is cited as approximately 15 megatons of TNT equivalent. Such figures highlight the immense destructive potential of the blast. The Tunguska event, a significant impact event, occurred in 1,908 inches Siberia. It is widely recognized for its immense energy release upon atmospheric entry. NASA materials consistently estimate the event's energy output. These estimates place the Tunguska event in the multi-megaton range. This classification highlights the extraordinary power of the atmospheric explosion. The energy released was comparable to a large thermonuclear weapon. This event was not a normal storm. It was distinct from typical earthquakes. It also differed from common wildfires. This event was not a typical natural disaster. This event represents one of the most powerful impact-related occurrences in human history. Its magnitude is considered unique among recorded historical impact events. The event's power highlights its profound historical significance. It serves as a benchmark for understanding the scale of past impact phenomena. The absence of an impact crater presents a significant enigma in understanding certain events. This key question challenges conventional explanations for high-energy impacts. Typically, an impact event of considerable force would leave a discernible crater. The lack of such a geological feature makes the event difficult to reconcile with standard impact models. This perplexing aspect suggests the need for alternative theories or re-evaluation of existing data. It is the most challenging element in explaining the nature and origin of the phenomenon. Scientists analyze celestial objects entering Earth's atmosphere. Many objects do not reach the ground intact due to atmospheric forces. Instead, these objects often undergo a process known as atmospheric explosion. This occurs when intense pressure and heat cause the object to fragment violently. The explosion releases significant energy, dissipating the object in the air. This phenomenon prevents direct ground impact, altering potential effects. An airburst phenomenon occurs when an explosion takes place in the atmosphere rather than on the ground. Such explosions typically happen at a significant altitude above the Earth's surface. This specific event is estimated to have occurred at an altitude of approximately 5 to 10 kilometers. The altitude of an airburst significantly influences its impact and observable effects. An airburst event occurs when an object explodes in the atmosphere before hitting the ground. This phenomenon generates a powerful shockwave that radiates outwards. The shockwave can flatten extensive areas, such as forests, without direct ground impact. Consequently, no classic impact crater is formed, resolving the paradox of widespread destruction without a crater. The asteroid airburst theory is a leading explanation for certain impact events. This theory posits that an asteroid entered Earth's atmosphere. Instead of striking the ground, the object exploded in midair. This explosion releases significant energy, causing widespread effects on the surface. The airburst phenomenon is a key focus in planetary defense and impact studies. Scientific consensus refers to the collective judgment, position, and opinion of the community of scientists. This consensus is reached through extensive research, peer review, and continuous validation of findings. NASA plays a crucial role in scientific research and disseminating information to the public. According to a 2023 NASA History article, a significant scientific consensus has emerged. Most scientists now agree on the classification of a specific celestial object. The prevailing view is that this object is indeed an asteroid, reflecting current scientific understanding. The comet airburst theory proposes a comet as the cause of certain impact events. This theory has been favored by some researchers for many years. A key aspect of this theory is the nature of cometary bodies. Comets are largely composed of ice and dust, making them fragile. Upon atmospheric entry, a comet would likely disintegrate and explode as an airburst. This airburst mechanism explains the absence of large recovered fragments at impact sites. The historical debate regarding comets versus asteroids has long been a topic of scientific discussion. Initially, the comet theory held significant weight in explaining certain astronomical phenomena. However, current scientific summaries increasingly favor an asteroid explanation. This shift indicates evolving understanding and evidence in planetary science. Fringe theories often propose unconventional explanations for phenomena. One such idea suggests antimatter as a cause for unexplained events. Volcanic activity is another exotic theory put forth by some. Some theories even involve alien spacecraft as a potential explanation. Others speculate about natural nuclear-like events as a cause. Public imagination often generates captivating ideas and theories. These concepts can gain significant popularity among the general public. However, popular ideas may not always align with established scientific understanding. NASA workshop materials highlight this distinction, noting such ideas are not mainstream. Scientific explanations are based on rigorous research, evidence, and peer review. Following the blast, witnesses reported unusual atmospheric effects. These phenomena were described as peculiar and unexpected. Subsequent reports corroborated initial observations of these atmospheric disturbances. The nature of these effects remained largely unexplained. This added an element of mystery to the post-blast environment. Following certain events, unusual atmospheric phenomena can occur. One such after effect is the occurrence of abnormally bright nighttime skies. This phenomenon was observed in specific regions, notably parts of Siberia. Areas of Europe also experienced these uncharacteristically luminous nights. The heightened brightness persisted for a considerable period after the initial event. Such occurrences are documented as significant environmental observations. The phenomenon of lofted material refers to fine particulate matter propelled into the atmosphere. This material is ejected to significant altitudes, often reaching high into the upper atmosphere. The presence of such lofted material is a key indicator for specific atmospheric events. It is consistent with the characteristics and aftereffects of an airburst event. The Tunguska event remained a profound mystery for an extended period. A primary contributing factor was the extreme remoteness of the impact site. This geographical isolation significantly hindered early investigative efforts. The difficulty of access prevented prompt and thorough scientific examination. The first scientific expedition to the site faced a significant delay. Researchers did not reach the location until approximately 2 decades after the event occurred. This substantial time lag introduced considerable challenges for investigation. The delay directly contributed to a lack of clarity regarding the event's details. Such prolonged intervals often hinder accurate data collection and analysis. Delayed arrival at a scene can significantly compromise the integrity of crucial evidence. Over time, environmental factors such as weather conditions can alter or destroy evidence. Natural landscape changes and biological processes also contribute to evidence degradation. These alterations make accurate analysis and reconstruction of events considerably more challenging. Significant delays in information or data acquisition can profoundly impact scientific understanding. These delays often lead to gaps in knowledge, making comprehensive analysis challenging for researchers. Consequently, many specific details about an event or phenomenon remain subject to ongoing scientific debate. The absence of timely and complete data perpetuates uncertainty and differing interpretations among experts. Modern scientific methods utilize advanced computational tools to analyze complex phenomena. Simulations are employed to model various scenarios, providing insights into physical processes. Impact modeling specifically reconstructs events involving high-energy atmospheric interactions. These computational techniques generate data that supports theoretical explanations. For instance, airburst events are studied through detailed simulations to understand their effects. This provides robust computational evidence, corroborating the airburst explanation. The Tunguska event caused a unique tree fall pattern across a vast area. Modern scientific simulations analyze this distinct pattern. These simulations provide explanations for the observed tree fall phenomenon. The findings corroborate the airburst theory as the cause of the Tunguska event. Scientific models are developed to account for various physical phenomena. These models specifically incorporate pressure wave effects, which are disturbances propagating through a medium. They also integrate thermal effects, which involve changes in temperature and heat transfer. The inclusion of these effects ensures the model's accuracy and comprehensiveness. This approach allows the models to align with and explain real-world witness accounts. NASA's supercomputer studies model atmospheric explosions. These models simulate events similar to the Tunguska explosion. The explosions are attributed to the breakup of incoming space rocks. This research enhances understanding of celestial object impacts on Earth's atmosphere. NASA conducts various studies to analyze celestial and atmospheric objects. These investigations often include determining the physical dimensions of observed phenomena. One such study focused on estimating the size of a particular object. The research indicated that the object measured tens of meters across. This finding provides a crucial estimate for its physical scale. Such size estimations are vital for understanding object characteristics and potential impacts. NASA studies investigate the energy release of celestial objects prior to impact events. Models indicate that the object released multi-megaton energy before ground impact. This pre-impact energy release is a critical factor in understanding destructive events. The calculated energy levels are consistent with observed destruction patterns. Such studies enhance our understanding of impact physics and planetary defense. Despite significant advancements in modern science, certain fundamental questions remain unresolved. One such question pertains to the definitive identification of celestial objects. Specifically, there is ongoing debate regarding the conclusive confirmation of certain events as asteroid impacts. The precise nature of these cosmic occurrences continues to be a subject of scientific inquiry. This highlights the persistent challenges in astronomical classification and event reconstruction. The cometary possibility remains a subject of active scientific discussion. Some researchers continue to consider the hypothesis that it may have been cometary. This indicates ongoing debate and a lack of definitive consensus within the scientific community. The cometary origin is one of several hypotheses still under investigation. The exact size of an object is a critical detail in many scientific and observational contexts. Despite advancements, determining precise object dimensions can remain a significant challenge. Factors such as distance, atmospheric conditions, or measurement tools can introduce inaccuracies. Consequently, the true scale of certain objects often becomes a subject of ongoing debate. This ongoing discussion highlights the complexities in achieving definitive measurements. A significant puzzle in historical and archaeological research is the scarcity of physical remnants. Despite evidence of past events or civilizations, tangible artifacts are often missing. This absence of physical proof presents a major challenge to understanding certain periods. The reasons for this lack of remnants remain largely unexplained. It is an unanswered question that continues to intrigue researchers and historians. The Tunguska event is a historical incident that continues to captivate public interest. Its fascination stems from the combination of a documented, real-world explosion. This event involved a significant atmospheric explosion near the Podkamenaya Tunguska River. The explosion occurred in Siberia, Russia, on the 30th of June 1908. The lack of an impact crater and the scale of devastation contribute to its enduring mystery. The concept of immense power holds a profound fascination for humanity. This allure often stems from the raw, untamed energy it represents. Such power can manifest in various forms, from natural phenomena to technological feats. The sheer scale of energy release, like in an explosion, commands attention and awe. This captivating nature is rooted in both the destructive and creative potential of great force. Understanding and harnessing enormous power remains a significant area of human endeavor and study. The absence of an expected impact crater presents a significant scientific enigma. This missing evidence adds a profound layer of mystery to the event under investigation. Impact craters are typically formed by high-velocity collisions of celestial bodies. Their absence suggests alternative explanations for the observed phenomena. Scientists are actively researching factors that could prevent crater formation. Delayed investigation refers to the postponement of examining a situation or problem. This delay can occur for various reasons, including resource limitations or initial oversight. When an investigation is delayed, initial facts may become less clear or harder to ascertain. The passage of time often obscures details, making resolution more challenging. Consequently, a delayed investigation amplifies the sense of an unsolved puzzle. The Tunguska event is a historical phenomenon, unlike mere legends or myths. Its occurrence is well documented and widely accepted as a factual event. This tangible basis distinguishes it from purely speculative narratives. The reality of the event underpins its enduring mystery and scientific interest. A significant event occurred in the Siberian sky, sparking a long-standing mystery. The core of the enigma is not the occurrence itself, but the specific details of what transpired. Investigators aim to reconstruct the exact sequence of events that unfolded above Siberia. This ongoing inquiry seeks to clarify the precise nature of the aerial phenomenon. The Tunguska event remains a significant scientific enigma over a century after its occurrence. A primary area of debate centers on the exact composition of the celestial object involved. Scientists continue to discuss whether it was a comet, an asteroid, or another type of body. The precise size of the object at the time of impact or atmospheric entry is also highly contested. Its fragmentation behavior, how it broke apart, is another detail that lacks consensus. These unresolved questions ensure Tunguska remains a topic of ongoing scientific and public fascination.